Hey everyone, welcome back to The Explainer. Today we are diving straight into the absolute core of EV safety design. We're going to tear down a super critical, high-stakes protection mechanism, the U019B fault code. If you're into system engineering, you know that managing high voltage requires, well, absolute precision. So we're going to look at the exact fail-safes that stop a DC fast charging session from turning into a total disaster. We're talking the whole anatomy of this global safety layer, from root causes all the way down to mass production validation. Let's get into it. So picture this. Your EV is plugged into a DC fast charger. The battery management system, or BMS, bypasses the usual onboard controls and is directly orchestrating this massive energy transfer with the charger. But what if that communication just drops? Or what if the protocol handshake fails? Suddenly, the car and the charger lose data sync, and that external charger is essentially pumping out power totally blind. We are looking at a huge risk of severe overcharging, internal lithium plating in the battery cells, and ultimately, thermal runaway. Total catastrophe. Now, staring down that thermal runaway risk, how much time do you think the system has to react? Half a second. Exactly 500 milliseconds. This tiny 500 millisecond window is the literal anchor for the entire failsafe protocol. Once that comms line drops, the car doesn't have time to second guess or try a lengthy reconnect. No way. It has to trigger a hard physical isolation within that precise window to save the vehicle.
Okay, so how do we end up in that terrifying situation in the first place? Let's break down the root causes.
The U019B fault usually boils down to two main culprits, electrical or physical. On the electrical side, you've got electrical overstress, EOS, and electrostatic discharge, ESD. Basically, the exact second you plug in that charging gun or those high-voltage contactors close, you can get these massive nanosecond-level voltage spikes. If your front-end protection isn't bulletproof, these surges will literally fry the communication chips or CAN transceivers, causing a permanent hardware open circuit. Then on the flip side, you have physical wear. Think about it. Constant plugging and unplugging plus road vibrations, this slowly chips away at the plating on the charging pins, causing oxidation and fretting wear. Over time, that physical degradation spikes the contact resistance, distorting the signal until it just completely drops out.
All right, so knowing these threats, let's look at the technical architecture. How does the system's immune system actually fight back? It all comes down to what engineers call a digital heartbeat. Every single data packet bouncing between the EV's charge controller and the external charger has a rolling counter and a CRC8 checksum baked right in. The BMS is working on a microsecond schedule, constantly verifying real-time voltage, current limits, and temperatures. Because of that CRC8 checksum, if any data gets corrupted by electromagnetic noise, even slightly, the system catches it instantly. If the heartbeat skips a single beat or the data's dirty, the system throws a red flag. And when that heartbeat flatlines, a standardized, safe power-down sequence takes over. It's actually a pretty dramatic microsequence of tension and release. Step 1, communication is lost. Step 2, as we mentioned, the BMS has a strict 500 milliseconds to trigger physical isolation, slapping open the high-voltage contactors and physically locking the charging gun so a panicked user can't rip it out during a surge. Then, step 3 is the tension. The system waits. It actively measures the current, waiting for that residual energy to bleed off. Finally, step 4, the release. Only when the current hits a safe level will it unlock the plug. This rigidly blocks any deadly electric arcs from forming. Obviously, we'd rather this sequence never have to fire at all. That brings us to the design phase, the preventative genetics of the system, or DFMEA.
Because the U019 comms failure knocks out the overcharge protection, which, remember, carries a massive safety severity rating of 7 to 9 due to explosion risks, designers have to protect those fragile communication lines. They use something called galvanic isolation. This is absolutely crucial. It's a physical, electrical shield made of high-precision digital isolators or transformers rated to withstand over 3,000 volts RMS. It acts like a massive wall blocking the chaotic, high-frequency switching noise of the fast charger from ever bleeding into the car's low-voltage network. It ensures the car can still hear that digital heartbeat even in a crazy, noisy electrical environment.
Plus, to handle those kilovolt-level surges we talked about earlier, the hardware uses TVS clamping. Think of transient voltage suppression diodes like heavy-duty shock absorbers for your electronics. They clamp down on deadly surges in nanoseconds, and they don't work alone. They're paired with RC low-pass filters in some really clever software. The software protocol is actually designed to forgive 3 to 5 error cycles. So if a random glitch drops a single packet, the car doesn't just panic and abort the charge. It maintains absolute safety without ruining your charging experience.
But great design means nothing if you can't build it right. Let's step onto the manufacturing floor and look at process control. At the end of the line, engineers don't just plug in a cable to see if the lights turn on. No, they run a dynamic contact impedance test. During a simulated handshake, they intentionally blast the charging port with micro vibrations. This shakes the pins to dynamically measure the impedance, specifically hunting for hidden terminal defects, bad crimps, or early signs of that fretting wear we discussed. They literally shake out the weak links before the car ever leaves the factory.
Finally, we reach the most brutal stage, validation testing, the DVP&R phase. This system has to survive an absolute gauntlet that simulates a lifetime of abuse. We're talking hardware-in-the-loop fault injection, where they purposely create open circuits just to test reaction times. They blast the comms lines with EMI noise, injecting plus or minus 8 volts at up to 150 kilohertz. Then they mechanically smash the plug in and out 10,000 times, throw the parts into an environmental chamber, and bake them continuously for 500 hours at temps swinging from minus 40 to 85 degrees Celsius at 95% humidity. It is intense. And the passing metrics? Totally unforgiving. These numbers are literally the boundary between a safe vehicle and a massive brand-ruining recall. When a fault is injected, the BMS must lock in the U019B fault code within a strict 1.0 second debounce threshold. Under that insane EMI noise bombardment, the data frames have to maintain a 0% CRC error rate. Zero. No false alarms allowed. And after all those 10,000 mechanical impacts and 500 hours in the swamp-like test chamber, the resistance of those pins has to stay strictly under 0.1 ohms. Which brings us right back to that final release condition we mentioned, the golden rule of EV charging safety, 1 ampere. Automated end-of-line testing guarantees that under absolutely no circumstances will the physical lock on the plug ever release until the active current drops below 1 single amp. It guarantees with 100% certainty that you can't yank out a live wire and trigger a lethal electric arc. So every millimeter of copper, every line of code, every single microsecond of timing, it all points to one singular goal, a 100% intercept rate for zero defect quality. The level of rigor in high-voltage safety engineering is honestly mind-blowing. It really makes you realize that charging an EV isn't just moving electrons around, it's a beautifully orchestrated, microsecond-perfect symphony of safety protocols. It kind of makes you wonder how many other unseen fail-safes are quietly working behind the scenes to protect us every single day. Keep learning, stay curious, and we'll catch you in the next explainer.